Okay, so this is chapter 1 of Giancoli's book, and we are going to start talking about measurement. Now, measurement is very important in physics and in any science. And the idea is whenever we make a measurement, we won't be absolutely sure about the answer. We'll have an answer with some accuracy, with some uncertainty associated with it. So the accuracy is related to the accuracy, to the limitation of the instrument. For example, if we go with our friend on a scale, and the friend comes out of the scale and tells us, today I'm 123 pounds. Nothing is that surprising, you'll be fine with this answer. But if your friend comes out of the scale and tells you that today she is, let's say, 123.85643021853 pounds, then you will be very surprised. Either your friend is playing with you, is joking, or that diet that she was on is really having an effect, is affecting her nerves. Right? So why would you be surprised by this number? Because of course that scale doesn't have that accuracy, right? So what you have to be careful when you write down numbers is how accurate is that number? How accurate was your measurement? All right, so let's come back to the notes. Here we have this number. Someone took a measurement and wrote down that the length probably that they were measuring was 5.2. And this person was very sure about this number 5, but not so sure about this digit. So 5.2 centimeters, but not so sure about this digit. So this person wrote 5.2 plus minus 0.1, meaning that the uncertainty is in the 2. This 2 could be 1 or it could be 3. All right, so we always, whenever you write a measurement, you have to write down the number, of course, of your measurement, the units, and the uncertainty. Okay, now there is this quantity that is called percent uncertainty, which is just a way to quantify how uncertain your measurement is. And how do we get that? Well, you do a ratio of the uncertainty divided by the value of your measurement. So here in this case we have 0.1 divided by 5.2, which gives us 0.02, which is 2%. So then we can say, well, this measurement has a 2% uncertainty involved with it. Okay? I'm not going to be very careful about this. These lectures, we are not going to be measuring anything, but in the lab, yes, in the lab you'll be very careful with the number, with the uncertainty that you're going to be associating with it. Okay? Okay, so now let's just play a little bit. As I said, this is not something that you'll be tested on, but let's just play a little bit with these ideas. Okay, so suppose you have a diamond and you weighted your diamond, and your diamond is 8.17 grams, but your scale, of course, has some limitations in the measurement that it gives to you, in the number that it gives to you, and you know that the uncertainty is 0.05. Okay, so then you wrote down in your notebook, my diamond is 8.17 plus minus 0.05 grams. And suppose you forget this diamond in a room, in a region that is not very safe. Many days passes and you come back to the room and you're very happy to find the diamond there. But you're not so sure that that is really your diamond. Okay, and you weight your diamond again, well, what you think is your diamond, you weight it again, and now this time the number that comes out is just 8.09. You use the same scale, and this time you get 8.09. So the question now is it the same diamond that you had before or not? Okay, so for this little exercise we have actually two questions. First one is, let's compute the percent uncertainty for this first measurement that you had done, and then let's agree or not whether this new measurement corresponds to that diamond that you had before. Okay, all right, so first let's do the easy one, which is to compute the percent uncertainty. Remember how we computed the percent uncertainty? We put the uncertainty divided by the measurement. So in this case here, 8.17 plus minus 0.05, what would be the percent uncertainty? We have here A, B, C, and D. So for sure, C and D are wrong, right? It's either A or B, because that's how we compute the percent uncertainty is 0.05 divided by 8.17. So this is the easy part of the question. Now comes the second one, which is many days passed and you're now weighing that diamond that you want to know if it's the same diamond or not, but this time you're only measuring, you're only getting this number 8.09. Is it the same diamond or not? Okay, so let's discuss this a little bit. If we go to the previous number that we had, the previous measurement that you had made many days ago, we know that 8.70 minus 0.05, which is looks like it's the lower limit, is just 8.12, while the upper limit for your measurement is something like 8.17. Okay, so then you see this lower value here, and you say, oh, 8.12 is not 8.09, so I'm in trouble here, maybe it's not my diamond. Well, but this 8.09 is an independent measurement, and it also has an uncertainty of 0.05 associated with it. That means when you measure 8.09, what that measurement actually means is something between 8.04 and something and 8.14. So the first measurement has an uncertainty of this 0.05, so that means something between 8.12 and 8.17. The second measurement that you took is between 8.04 and 8.14. It is a bit suspicious, right? Because the maximum here is 8.14 and 8.12 for the previous measurement, but there is an overlap. So that means it could still be your diamond. So the answer would be B, meaning, well, it could be. It may not be, but it could be. Now, based on the two measurements and based on the uncertainty associated with that, we cannot be totally sure. All right, very well. So let's come back to the lecture. As I said, I'm not going to be too concerned about these issues, about the uncertainty of the numbers, because we are not going to be making measurements, but in the lab you will have to be very, very careful with these things. Okay, let's move on. Now, the idea of significant figures. This is very important. Okay, we can never write down a number with more numbers than our accuracy. Now, we cannot write digits that are not justifiable. Okay, and how do we count what are the numbers, the digits that are justifiable, they are relevant, they are significant figures? Okay, let's have a look at this number here. If someone wrote 23.21 centimeter, it means that this person has accuracy, has knowledge of all of these numbers. Okay, so then we'll say, well, this number has 4 significant figures. Okay, now these are the number 23.210. If the person wrote this 0, well, this person can justify that. It is related to the accuracy of the measurement that he or she did. Now, so here we have 5 digits, 5 significant figures. That means this measurement here was done with one equipment. This other measurement was done with a more precise equipment. All right, a more accurate instrument. Okay, so whatever we write down, we have to be able to justify. So we have to have behind it an instrument that really gives all of these digits. Okay, now when the zeros, so a 0 that is on the right is really a significant figure, is an important number. We only write it if we know that, if we can justify it. Okay, now when the zeros come before, on the left, then they are not significant. See, when I write this number like this, 0.062 centimeters, the number of significant figures here is just 2, because everything that comes before is not associated with accuracy. Everything that comes before is just associated with the units. What do I mean here? You see, the number 0.062 centimeters can also be written as, let me come back here, that same number can be written as 0.62 millimeters, right? So 0.62 millimeters and 0.062 centimeters are the same numbers. So you see that this additional 0 here is not a significant figure. It's just a consequence of the unit that I was using. All right? Okay. Now, another important point, let's come back to the notes, is when we write a number like this, 8 and 0. Okay, so the 0 is on the right. So in principle, if we come back to what we said before, this is a significant figure, but there is no point here. So then I cannot be sure whether the person meant to say that that 0 is or not a significant figure. If the person really wants to say that that 0 is a significant figure, came from a measurement, then the best way is to write 80 and put a point there. Then I know for sure that the two numbers are significant. When I see a number like that, then I'm not totally sure. It could be just that the 8 is significant or the 8 and 0. All right, a number like this. Oh, so here, how many significant figures we have? Then for sure we have 3. Okay, otherwise the person would not have put this later 0 there. Okay, so this I'm not going to be checking if you are able to count how many significant figures and things like this. But what is important here is keep in mind, do not put too many numbers. Do not put digits that you cannot justify. Let's go now to computing areas, for example. Now, when we have two measurements, we measure the width and we measure the length of an object, and we want to compute now its area. So how are we going to be dealing now with this significant figure? So suppose we measure the length and we got this 11.3. So I can justify all of these numbers. All of these numbers came from my instrument. And we computed the width and we got 6.8, and I can justify all of these digits. Okay, so everything came from the instrument that I used. And now I want to compute the area. So we know that the area, I'm going to multiply these two numbers. All right, these two numbers which are in centimeters, so my area will be in square centimeters. All right, so how are we going to do this? If I just put in my calculator 11.3 multiplied by 6.8, this is the number that we are going to get, 76.84. And is this the way I'm going to give my answer? Should I write 76.84 square centimeters? Well, look, this is very suspicious because the accuracy of the numbers that we got the accuracy was the number right before the dot. Was at this point. And now the number that I'm getting has 2 digits after the point. Also, these numbers that I had, this one had just 3 significant figures, this one had just 2 significant figures, and I'm giving now a number with 4 significant figures. This all sounds too much. Let's think a little bit more about that. If I wrote these two numbers, I know that the accuracy for this number is in the 3. So I wrote 3, but well, it could be close to 2, right? And this other number I wrote 8, but wow, there is an uncertainty there, so it could be 7. So if I put these lower limits for my two measurements, I would get an area that would be 75.04. Okay. Now, if I put the upper limit for these two numbers, I would use 11.4 6.9, and I would get 78.66. So you see there is a big gap between these two numbers, a wide, a broad range. So what is now, come back to the question, what is the area that I should write? Well, I'm in between these two extremes, between 75 and something pretty close to 79. So what is the medium between 75 and 79? Well, then the best answer is something around 77 without digits after the point. Okay, so this is the way I would answer the way I would give the value for that area, 77 square centimeters. Okay, but there is a rule for that. If you didn't follow this well too much, there is a rule for that, and the rule is the following: whenever you're multiplying or you're dividing numbers, use for your answer as many digits as the number with the least number of significant figures. That's what I did before. Let's go back. Here we have 3 significant figures. Here we have 2 significant figures. I multiplied and then I wrote my answer with just 2 significant figures. Okay, this was my number, but how can I write this number with just 2 significant figures? Well, this is pretty close to 77. Okay, whenever what comes after the point is above 5, then I'm closer to the next number. So instead of writing 76 here, I wrote 77. Okay, because we are closer to 77 than to 76. All right, so this is the rule. If we are multiplying or dividing two numbers, how are we going to give the answer? Check the two numbers and count the one that has the least number of significant figures, and that's how your answer will be. Okay. Now, if you are adding or subtracting numbers, well, if you are adding or subtracting numbers, there is also a rule, and the rule is the result cannot be more accurate than the number with the least accuracy. What do we mean by that? Suppose we have a certain subtraction, let's say. So I'm subtracting the number, oops, not here, let me subtract the number here, 3.1 minus 0.99, okay? So this first number here has accuracy at 1. This other number here has accuracy 2 digits after the dot, okay? What is going to be my answer? Well, my answer is, if I just put in the calculator, 2.11. Okay, but the number that has the least accuracy is this one. No? It ends in 1. So how am I going to answer? How am I going to write the answer? Just 2.1, because the accuracy, the one with the least accuracy is this one, has just one number after the digit. So I'm just going to consider one number after digit. Okay. All right, so coming back to the notes. Again, I'm not going to be checking if you counted correctly the number of significant figures, okay? This is just for you to have a good idea. In the lab, again, these things will be important. In the lectures, not so important. What is important now for the lecture? Scientific notation. Okay, scientific notation, then yes, this is something I will check, and yes, you should know. Okay, and what is scientific notation? Well, a way to write our numbers in powers of 10. This is very useful when your number is very, very large, or when your number is very, very small. So the powers of 10 can help us a lot. So for example, we have here this number, 2,321, and I want to write it in terms of scientific notation. I want to write it in terms of powers of 10. How am I going to do that? Well, I can write this as 2.321 10 to 3. 10 to 3 is 1,000, right? So if I multiply 2.321 by 1,000, I recover my number. So this makes sense. So how did I come up with the idea of putting this 3 here? Now, these powers of 10, how did I come up with this exponent 3? Well, this is my number, and what I did is I went on counting. I started here from the right, and I said, okay, I'm going to put a dot. So let me go 1. Okay, 1. 2, 3. So if I decided to put the dot here, I have to multiply this number by 10 to 3. Okay? Okay, what do we do now if I want to move my dot to the right? Okay, if I move it to the right, then my power will be negative. Okay, so for example here, this number 0.0062. This number is equal to 6.2. 6.2 is a big number, much bigger than this. 6.2 multiplied by 10 to minus 3. What is 10 to minus 3? 10 to minus 3 is 0.001. So if I multiply this small number, 0.001 by 6.2, I'll recover my small number. Okay, so how does the rule go? If I'm moving to the right, I have to count as I go to the right, but I will have to add a negative number. Okay, so I counted 1, 2, 3. So now I can write this number as 6.2, but to the power 10 to minus 3. Okay, so let's repeat. When I'm moving my dot to the left, I add here 10 to plus a number. No? So in this case, 1, 2, 3, 10 to 3. When I move my dot to the right, then I count 1, 2, 3, but minus 3. Okay, so if I go to the right, it's negative. If I go to the left, it's positive. No? To the left, the number has to increase. To the right, the number has to decrease. The power has to decrease. All right? Okay. Now, if I give you this number, 36,900, and I didn't put any dot anywhere, how can you know what the accuracy is? Well, if you write it in terms of, if you use the scientific notation, then we know the accuracy. If we write this number as 3.69 10 to 4, then we know that these two zeros were not part of the accuracy of my measurement. Okay, so the scientific notation is very helpful in this sense. Okay, now why did we put 4? Let's see. We are moving the dot to the left, right? So I started from here, 1, 2, 3, 4. So that's why it's 10 to 4. Okay, if I write this number like this, 3.690 10 to 4. Oh, if I see that, then I now know for sure that that 0 is part of the accuracy. No? And here, I used a different instrument to make this measurement where these two zeros are already part of the accuracy. No? So the scientific notation helps us know what is the accuracy of a number given like that. Very well. Now let's move to units. Okay? And this is very, very important now. Okay, so scientific notation is something that I do expect you to know. And now units. Units is key to any science. Okay? Whenever you write a number, you have to tell us what is the unit of this number. If you just write number 2, and if you don't tell me if it's 2 meters, or it's 2 hours, it's 2 centimeters, I will be very upset. I'll cut something from the question, okay? So whenever you give me an answer, you have to tell us what is the unit, okay? So it makes a total difference. Very well. There is something that is known as International System of Units. It's called SI system. And why, you may wonder why it's called SI, right? Because it's IS, so why do they call SI? Well, this is because the word came from French. No, it's Système International. Anyway, the SI system, the International System of Units, tells us what is the basic unit, what is the unit that we are going to use for length when we are measuring the length of something. Then, in this unit, the length will be meters. Okay, of course, we can measure length in centimeters, we can measure in miles, in kilometers, and so on. But if they tell you this measurement the answer for this measurement should be written in terms of the International System of Units, then you know you'll have to write it in terms of meters. Okay? Okay. What is the unit used for math? From the International System of Units, what is the unit for mass? Well, kilogram. Again, when you are weighing something? Well, the answer could be in pounds, could be in grams, but if they want you to give it in terms of the International System of Units, you will write in terms of kilogram. Okay, how about time? Time in the international system is written in seconds. Okay, there are other quantities here in this table, but we are not going to talk about them because we are not going to be seeing them in this semester. Okay, so all that you have to care about are these three, and you have to know that the International System of Units for these three quantities means meters, kilogram, and second. Okay, now these are called basic quantities. There are also quantities that are derived. For example, velocity. Velocity is a derived quantity because velocity is written as meters per second. Okay, but you'll see velocity and acceleration, other things are coming up later. What you need to know is only these three for the moment. Okay, let's talk a little bit about length or distances. It's really impressive, how the universe is. Look at this, an atom. The length of an atom is approximately 10 to minus 10 meters. It's extremely small. And you see how useful the scientific notation is being to us here, because imagine writing 0.00001. It would be a very long number to write. So the scientific notation was very useful here. So an atom is something extremely small, while if we go to cosmological length, if we start thinking about the universe, then we find extremely big numbers. Now the distance from the Earth to the Sun is 10 to 11 meters. Again, the scientific notation was helping us a lot. Anyway, all this is written in the International System of Units. Now all of these lengths are written in meters. But if you don't want to write such big or such small numbers, you can try to look for a prefix. A prefix, for example, the length of a neutron or a proton, the radius of a neutron or a proton is approximately 10 to minus 15 meters. Well, instead of writing 10 to minus 15 meters, you can give a prefix to this 10 to minus 15 and write it in terms of this prefix. So, if you come to this table, you will see that 10 to minus 15 is called femto, F. So, you could write the size of your neutron. Instead of writing 10 to minus 15 meters, you could just say, well, the size of a neutron or a proton is approximately 1 femtometers. Okay, so these are the prefixes that are available. Okay, of course you don't have to know them. Do not memorize them. Nobody knows all of them. No? But there are some that, of course, you must be familiar. Now, the ones that are very much used, such as kilo, right? Kilo is 10 to 3. So this one you should know. You will be using a lot, and you probably already know. Another one that is very important from this list that you will be using and that you should know, centi. Centi is 10 to minus 2. No? So the abbreviation is C. When you put C with M, you get to the centimeter, so it's 10 to minus 2 meters. Okay, milli. Milli is also very important. If you put M, you know that you're talking about millimeters. If you're talking about liters, then you could talk about milliliters. All right? So, kilo, centi, and milli are very important. Other prefix that are important for you. Well, in biology, of course, micro is very important. Now that's the size of the microorganisms, the size of the bacteria, is of the order of micrometers. Another two that are very popular nowadays because of computers is mega and giga. Now we often talk about megabytes or gigabytes. Okay, so these 6 ones, yeah, I do expect you to know, but the others no. No, 6, no, 7. Right? Giga, mega, kilo, and then centi, milli, and micro. Yeah, so these are 6. So these 6 ones you should know. The other ones not so important. All right. Now, how about time? Well, human beings have always been obsessed about trying to measure the time. And we develop different instruments to try to count the time that always just moves forward. There is a very nice book called Longitude by Deva Sobel, and this is the whole history of this person who was a carpenter, and Harrison, trying to develop a very accurate clock. And this was very important because that was the way to know your longitude. Now, if you don't know your longitude in the sea, you cannot know very well where you are. So it's a very interesting book. If you have time, read it. I really suggest it, recommend it. It's a very nice book. Very well. So when we talk about time, what are the units for time? Well, we can talk about times in minutes, we can talk about time in hour, we can talk about time in seconds, we can also talk about time in years, in decades, in centuries, and so on. And it will be very important for you to know how to convert, okay? So how to change from one unit to the other. So if we have 1 hour, how many minutes would that be? Well, then you know that in 1 hour I have 60 minutes. Okay? In 1 minute, how many seconds do we have? Well, in 1 minute we have 60 seconds. Based on that, then I can ask you, well, so how many seconds do we have in 1 hour? Well, then you just multiply 60 by 60 and you get 3,600 seconds. All right? So what I'm doing now, when I'm converting from hour to second, basically I'm doing a conversion. I'm converting units. And this is now the main point of this chapter. Okay, so I'm going to repeat. Knowing how to convert units is the main topic of chapter 1, and you will be using throughout this semester and also next semester. Okay, it's extremely important to know how to convert the units, not the conversion factors. Okay, the conversion factors in many cases I will give to you, but knowing how to convert, yes, this is very important. Okay, so what do I mean by that? The conversion factors. Well, how to convert from kilometer to meter? Yes, this you're expected to know, no? Because these are the prefix that we talked about and that you should know. Okay, how to convert from hour to seconds? Yes, this one you should know. No, because the conversions in time you should know. Now everything that comes below, then it's not so important. Okay, it's not important the factors, but how to convert, it is important. Okay, so if you don't know that in 1 mile we have 1,609 meters, that's fine, because I'll tell you. If we have an exam, I'll tell you, I'll give you this conversion factor, but then you will have to know how to do the conversion. Okay? If you don't know how many centimeters are in 1 inch, don't worry. You can Google it, now you can look in a book, and if it's in an exam, it will be given to you. Okay? So these conversion factors you don't need to know because you can always find them, but you will need to know how to convert units. So this is what we are going to try to do now. Okay? So let's see. Let's start with this problem here below. We have someone driving at 55 miles per hour, okay, miles per hour, and we want to write this number in meters per second, okay, ms. All right, so we want to write this speed in terms of the International System of Units. We want to write this speed in the SI units. Okay, so how are we going to do that? It's described here below, but let's do it together. Okay, so let me write the number here. The number is 55 miles per hour. I want to get rid of the mile. How am I going to get rid of the mile? Well, to get rid of that, let me put this a little closer to the right. So to get rid of the mile, I'm going to put this mile below here, 1 mile. Okay? Because I want to cut them. I want to cut the mile from my number. I cannot just do that like this. I have to put something here in the numerator, And what should I do? What should I put in the numerator that is equal to 1 mile? Well, 1 mile, if you look at the conversion there, is equals to 1,609 meters. Okay? So I multiplied and divided by something that is equal. So this is not affecting really my number. Okay, so I'll be able to cut my miles. Now I want to cut hour. So how am I going to cut hour? I'm going to put hour in the numerator because then I can cut with the hour that is showing up in the denominator. But I cannot just do that. What is 1 hour? Well, 1 hour, as we said, is 3,600 seconds. Okay, so now this looks good because I'm going to cut the mile that I didn't want. And I'm going to cut the hour that I didn't want. And now I have my number written in meters per second. So what we have to do now, well, we have to multiply, put in your calculator, 55 multiply by 1,609, and then divide this number by 3,600, and you will see that you will get 25 meters per second. Okay? So then you were able to convert the number, the speed that was written in miles per hour in meters per second, and this is what you see there in the notes. All right, now let's try to do another exercise. The exercise now is to do the opposite. We are now, well, not really the opposite. We want to convert 5 meters per second, okay? So 5 meters per second to kilometers per hour. So how are we going to do that? So let's go back to the idea. We want to convert 5 meters per second. So this is a new problem. 5 meters per second now in kilometers per hour. Okay. So first thing, I want to get rid of the meters. How am I going to do? I have to put these meters here below. Okay. Now, what can I do? Well, I can put 1 meter here, and I have to write it in kilometers. Let me go back to my conversion factors. 1 kilometer is 1,000 meters. So I can say that 1 meter is 0.001 kilometer. But wait a second. Why would I do it like this? Playing with these tiny numbers. No. Let's make our life easier. Look how we could do this. The same thing, okay? And it's going to give us the same result. But a more clever way is, I want to get rid of the meters. Okay, put meter there. But let me use as it's written here in the conversion factor. Let me just put here 1,000. 2, 3. And here 1 kilometer. And this looks much easier than writing this tiny number, right? Okay, so this is good. The meter is almost done. Now let's also get rid of the seconds. How are we going to get rid of the seconds? So now I have to put the seconds on top, right? Because the second is appearing below, I want it on top. And I want hour to show up. Let me look at my conversion. I know that 1 hour is 3,600 seconds. So I'm going to put 1 hour here, which is equal to 3,600 seconds. And now I'm happy because now I can get rid of the meters. I can get rid of the seconds, and I'll get my answer in kilometers per hour. So now what you have to do, put in your calculator 5 multiplied by 3,600 divided by 1,000, and you should get that value here, 18 kilometers per hour. Now, so you see, in the note, I did use that first way that I was trying, okay? But so now you have two ways. Either you put 1 meter is equal to 0.001 kilometer, or you do as we did now, 1 kilometer is equal to 1,000. This is all equivalent, all right? Okay, let's continue. Another interesting point of this chapter is what is called order of magnitude. The order of magnitude is not something that you will be tested on, not at all, but it's a fun thing to do. It's like a game. It's a rough estimate of some measure or something that you are trying to quantify. For example, you enter a room and you want to get an idea of the volume of that room without having to go and measuring it. Now, suppose you want to buy an air conditioning, and so you need to decide which air conditioner you're going to buy. You have to have an idea of the volume of that room. Now, so you have to have an idea of the width, the height, and the depth of the room. So just by looking, you can get an estimate. Now, people who have built their houses, or architects, engineers, they have a very good sense for that. And they enter a room and they immediately can say what is the volume, or what is the area of the piece of land that you're going to buy. So this is what we're going to try to do now. Just a little game, okay? And we are going to try to estimate the volume of our textbook, okay? Again, I'm not going to be testing you on that. We are just having fun now. Okay, so here is our book, okay? And we want to estimate its volume. How could we do that? Well, to estimate the volume, we have to have an idea of what is the width of the book, and what could we say? Maybe something around 20 centimeters. Well, to say that, you also have to have a notion of the unit. So if you're not much used with centimeters, you may not be able to do that. So you may prefer to do this exercise in terms of inches. But I'm telling you, so something around 20 centimeters. It may be 18, maybe 17, maybe 21. I don't know. It's approximate. Okay? How about now the height? What is the height of the book? I don't know. I think it's something around 30. I'm guessing that, okay? And then finally we have to know what is the width. The depth. So what could be the depth? Well, have a look, and I would tell you something around 2 centimeters, okay? Well, if you prefer, do that with inches. So based on this estimate, then I can estimate the volume, right? So I said 20 centimeters, 30 centimeters for the height, 2 centimeters for the depth. I multiply all that and I get something as 1.2 10 to 3 cubic centimeter. I'm not going to put that 1.2 here, right? 2 multiplied by 3 multiplied by 2 is 12, but I'm not going to put that 1.2 there because this is an estimate, so it's roughly 10 to 3 cubic centimeters. All right, okay, now let's do another game. Let's estimate the thickness of one piece of paper of our textbook, okay? Now, one piece of paper, how many pages does it have? 2, right? One page on one side, one page on the other side. Okay, so I'm going to write this down. In one piece of paper I have 2 pages. How many pages do we have in our book? Well, I'm going to go all the way to the end of the book and I'm going to count. Well, let's see, something around 400. I can read 420, so there are some additional pages there, so I'm going to say something around 500. Okay, so look at the information that we have. We already estimated the volume of the book, right? We know that in each piece of paper we have 2 pages, and we know that in the book we have approximately 500 pages, so that is, we have actually 500 pages, we have actually something around 250 pieces. Okay, so what do we have? We want to know what is the thickness of one piece of paper. Okay, so this is my unknown. I have 250 pieces of paper in this book, and these 250 pieces of paper gave us approximately 2 centimeters. Now the thickness, the depth, the thickness of this whole amount of 500 pages or 250 pieces of paper is 2 centimeters. So what is the thickness of a single piece of paper? Well, 2 divided by 250, which is approximately 0.1 millimeters. Okay, so this is all just an estimate, a little game. So repeating the story of the thickness of a piece of paper in the textbook. I knew how thick the book was, right? I knew how many pages the book has approximately. Now I have to be careful because in each piece of paper we have 2 pages, and I want to know what is the thickness of a single piece of paper. So 500 pages means 250 pieces of paper, and so 250 pieces is 2 centimeters. I wanted to find out the thickness of a single piece of paper, and that's approximately 2 divided by 250, which is approximately 0.1 millimeters. Okay, so it's approximately, you see, if you compute that, you get this number, which is approximately 0.01 centimeters, which is then approximately 0.1 millimeters. Okay, all right. This was just a game. Again, you are not supposed to know these things. You're not going to be tested on this. This is very vague. This is just to play with. Okay. Now, finally, something that you will be tested on, something that is very important for this chapter, which is known as dimension analysis. So what is dimension analysis? Dimension analysis is something for us to find out if an equation is correct or not. And scientists do this a lot. Now, sometimes you go to a conference and there is someone there sleeping the whole talk, doesn't pay attention to anything, but almost at the end of the talk the person wakes up, looks at the slides and says, oh, this is wrong. This result must be wrong. And then you wonder, how come this person was so fast? Now, was he or she following the whole talk in his dreams, in her dreams? Well, the answer is not that. The person just did what we call dimension analysis. Now, just by checking the units of the equation, the person can say if the equation is right or wrong. So, let me try to explain this. I'm going to give you an equation. You have no clue what that equation is, but I'll tell you that each symbol in that equation has a certain unit associated with that. So this is the 2 equations that I'm giving to you. Okay, so symbols there. And this V here, it stands for velocity. Okay, and I'm going to tell you, you have no clue where these equations came from, and you don't know which one is right, but we want to find out which one of these 2 could be right. Okay, and we are going to compare the units on the left with the units on the right. Okay, so what I'm telling you, V here stands for velocity, and I'm telling you velocity is given this unit, meters per second. All right, meters per second. On the right, we have these other 2 quantities, A. A here stands for acceleration. And I'm telling you, acceleration, the units for acceleration is meters per second square. All right? There is another symbol here, it's T. T stands for time. And the unit for time is second. Okay? So, based only on that, we'll have to figure out, we'll have to choose which one of these equations could be right. And we'll have to say which equation is for sure wrong. Okay? So how are we going to do that? We are going to compare the units on the left with the units on the right. Okay? We want to know if the units at least are making sense. So we said that velocity is given in meters per second. So this is the unit that we have on the left. Okay, how about on the right? On the right, we have the unit for acceleration, for the A, meters per second square. So I'm going to write this here, meters per second square. Okay, and I'm thinking now about this first equation. The other term that it appears is time. In this equation here, time is squared. So time is in second, and since it is squared, I'll put here second. Okay, so this is what we have on the left. This is what we have on the right. Is this equal? So my question is this equal? Well, look, second square cancels with second square. And for sure, meters per second is not equal to meters. All right? So, for sure, that first equation is wrong. So this first equation is dimensionally wrong. Let's go to the next equation where we wrote V equals to AT. So on the left we have meters per second. We want to know if this unit is or not equal to what appears on the right. So acceleration is meter per second squared. Time is in seconds. Okay, so now I cancel one time with one time here, now 1 second with 1 of the second square, and now we end up with meters per second here. And here we also have meters per second. So what we can say for sure is that this equation is dimensionally right. I'm not sure if this equation is exactly correct, because to know if this equation is exactly correct, there might be a number 2, or a number, or it may be divided by 3, or it can be added by another number. That would still be dimensionally right. Okay. So all that I can say is that this equation is dimensionally right, and that this other equation is dimensionally wrong. And dimensional analysis, as I told you, is very important to find out if an equation is right or wrong. All right. Okay. Let's do some more problems just to finish this chapter. Okay, so here the problem is to calculate the area of a rectangle that is, let's do that. The area of a rectangle that is 4.5 centimeters, and so this is the width, no, the length, and the width is 3.25. Okay, so let's multiply that to get the area. And this is the number that my calculator is going to give. How are we going to enter the answer for this area? Am I going to put all this in square centimeters or not? The answer is not. Why? This number has only 2 significant figures. This number has only 3 significant figures. So I'm not going to enter my answer with 5 significant figures. I'm going to choose the one that has the least, which is just 2. So I'm going to enter my answer as 15. No, 14.6 is closer to 15 than to 14. So I'm going to answer as 15 centimeters centimeter squared. Okay, so this is the answer for this area. Okay, another question. These two numbers, do they have the same number of significant figures? Well, let's count. This one has 1, 2, 3. Remember, we do not count the zeros on the left. So this one has 1, 2, 3 significant figures. This one has 1, 2. I do not count what comes the zeros on the left. So no, the answer is no. They do not have the same number of significant figures. This has 3, this has 2. How many significant figures are in these numbers? Well, 1, 2, 3, here, 1, 2, 3, here, 1, 2, 3, right? I do not count the zeros on the left, so they all have the same number of significant figures. Okay, now comes another problem of conversion of units. We have a driver driving at 15 meters per second in a zone where the speed limit is 35 miles per hour. No? So this is someone who came from Canada. His car gives him the speed in meters per second maybe, and we want to know if he's exceeding the speed limit or not. Okay, so let's convert that. Okay, so how are we going to do to convert? Well, let's do the same story as we were saying before, right? I have here, which one should we do first? Well, you can choose. Either you're going to convert 15 meters per second into miles per hour, or we can convert miles per hour into meters per second. I'm going to choose this one. I'm going to start with 35 miles per hour, and I'm going to try to convert it into meters per second. So let's come back to our conversion factors, right? So we want to get rid of the miles, so I'm going to put 1 mile here. I know that 1 mile is 1609 meters, right? So I'm going to put here 1609 meters because I want to convert it to meters. And I know that 1 hour is 36 seconds, so I'm going to put 1 hour on top, divided by 3600 seconds. Alright, so now I can cancel the hour, now I can cancel the mile, and now I have to multiply 35 by this number, divide by 3600. Let's do here in our calculator, right? So we have 35 multiplied by 1609 divided by 3600, and we get 15.6. Okay, so let's come back to the problem. We got here, I'm going to write the number, we got here approximately 16 meters per second. Okay, so 35 miles per hour is approximately 16 meters per second. And this person is driving at 15 miles per second, so that's fine. Huh? He's not going above the speed limit. He's almost at the limit. Alright, this is the end. Let's just summarize what we've seen in this chapter 1. We talk about measurement. We said that every measurement has an uncertainty. I'm not going to be picky about that because we are not going to be making measurements in the lab. Yes, you will have to be very careful with that. But what I'll look is if you do not put too many significant figures. Now, if you enter an answer with just too many numbers after the comma, that do not make sense, then I'll be a little, I may cut that. But otherwise, I'm not going to be too strict if you counted exactly the correct number of significant figures. What is important in this chapter? Scientific notation. Yes, you have to know. Extremely important in this chapter. You have to write your numbers, your answers with a unit. If you do not put a unit, then you will lose points in your problems, okay? So you always have to put a unit. To what? To hours, to years, to kilometers, to meters per second. You have to put the units, okay? And today we talked a lot about the units from the international system, which are meter, kilometer, and second. Another very, 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 very important aspect of this chapter. You have to know how to convert units, how to go from miles per hour to kilometers per second, to meters per second, and so on. You have to know. You do not need to know the conversion factors, but you need to know how to do the conversion. Order of magnitude. We talked a little bit about this, now how to estimate the volume of a room, the volume of a book, and so on. This is not important. This is just a game. You're not going to be testing on that. Another extremely important thing for this chapter, and you will be tested on that, is dimension analysis, which is a very useful way to find out if an equation is wrong. We can never know exactly if the equation is correct, because there could always be some constants involved, but we can at least know if the equation is incorrect. When we wrote these two equations, we knew for sure that the first one was wrong, dimensionally wrong, because the units on the left did not match the units on the right. So that's it for today. Thank you.